Hello everybody and welcome to this module. In this module we're going to discuss the infinitesimal deformation. You might have heard of this, but here we're going to talk about the origin of the infinitesimal deformation. So we're going to develop some mathematical kind of formulation which lands us finally in infinitesimal deformation. And I hope that you enjoy this lecture because this is basically the first lecture that you're going to touch somehow physically the strain concept and the strain concept that you learned before in mechanics of materials. So it's going to be, you know, a lot of fun. So let's get started. First, we're going to uh, basically develop the mathematical preliminaries for the infinitesimal deformation. And for this, we start from the previous session where we had two, configuration, if you remember. So we had a current configuration, and then we had, let's say, a deform configuration or current configuration. So this was basically the reference configuration. And then we had the current configuration. All right. So we already said that we have a kind of a region here. So maybe x1, x2. And we said that we have kind of like a vector where we use the capital X. So this is the initial or the base or reference configuration. And we have the deform configuration right over here, small x. So this is our particle, for example, p at t equal 0. And here it's our particle at, for example, after time t. So this vector here, which is u, and can be both described in, both in material as well as, a spatial coordinate system, is basically the displacement vector here, or the displacement field here. So simply, you can see from this figure that x, if you remember x, which was basically a function of capital X, so small x was a function of capital X, and t is equal to the summation of x, this vector, this initial configuration here, where we had this particle here, plus u of x and t. Therefore, you can simply write u of capital X and t is equal to x, small x, which is a function of capital X and t, minus x, which is basically the function of capital X and t0, but we simply just write x here, capital X in here. So this is basically in material coordinate. But you can write it in a spatial coordinate. So u becomes a function of a small x, t is equal to, and now we have x minus, now x, capital X, is a function of small x and t. All right, so this is basically our displacement field in here. So the next preliminary topic is the kinematic for the rigid body motion, or the kinematic equation for rigid body motion. So you can remember from your dynamic course where you had this kind of translation uh, kind of movement, for example, and you also had this rotation. So we're going to discuss this in continuum mechanics and develop their mathematical kind of, models. So where you have, so if we have the rigid body, for example, translation, rigid body translation. So the deformed configuration will be the sum of the initial or reference configuration plus some function of time. So this is only this function only is a function of time. So if you have the time t equal to 0, so this c is c at, at 0, or for example, c at, or simply 0. So you have the reference and the current configuration on top of each other. And we can prove here that if you remember, it was u, the displacement field was x minus x, small x minus capital X. And if we just replace from here, ct minus x, we get ct. So everything is a function of time. So we can say that if you have, if you have a material point, or if you have a particle point in, in your configuration here, and if you translate it using the rigid body translation, so everything is just changed from one place to another place. So if you have, for example, your initial configuration like this, so it is just translated to, for example, here, or for example, in vertical direction, or in horizontal direction. So the magnitude does not change, and it is only a matter of time. It is only a function of time. Like if you remember, you had a car in dynamics, and you said that, okay, so it translates at time, so it starts time equal to 0, and after time equal to 1 second, so it is here. So basically it did not deform. Basically, it just translated from one configuration to another. All right. Then we have the rigid body rotation. Body rotation. So for the rotation, we can use x equal to a rotation, or an orthogonal tensor, or rotation tensor, times x. Here, the capital X. So you have your current configuration, you have your reference configuration times a rotational tensor, and you get your current configuration. We also had this in, let's say, in your previous course, like mechanics of materials. If, for example, suppose that you had a tensor, or you had a vector, and you use a transformation tensor to transform it into, for example, something else, right? So this is the same, let's say, not the same notation, but like the analogous concept. So this is the same as here. But if this is when your rotation, your center of rotation is origin. So origin is the center of your rotation. Sorry. The center of rotation is at origin. Is at origin. So if it is not, then you have, a diamond like kind of vector here, like B, where you can say that, okay, this is my, for example, if you have something like this, this is your coordinate system here, you're at origin, and then, for example, you rotate your configuration like this. But if your current configuration is here, so you have a vector like B, for example, and it is rotated like this. So you see that you have to subtract B to somehow translate the origin from here to basically here. So this is, that concept behind this, where we use B here. All right. We can also show that, so the book also showed this in example 3.61, showed that even with rotation, the dimension of your current reference configuration, it does not change. So if it is 1, 1, so it will remain 1 and 1, for example, here. We can do this. It is very, very simple. So if we have, let me write this here, maybe with another color. So example 3.6.1. Here, the aim of this example is that, so rigid body rotation basically does not change the distance between between any pair of material elements, any pair of material points, sorry. So suppose that you have a configuration like x1 minus b is equal to, so I'm just writing this here, rt x1 minus b, and you have also another, let me just this bit to the right. So this is your first point, and you have also second point, x2 minus b, so r t x2 minus b. And what I mean by this, so you have a point like point 2, so you use this rotation, rigid body rotation, basically here, to transform it to to a small x2. I hope you get it. So now I'm gonna say that, okay, due to this, rigid body, because of this rigid body, basically this rigid body rotation does not change the distance between any point in our configuration. So for this, I'm going to write x2 minus x1. So I just subtract these two from each other. So maybe I write this 2 and this is 1. So 2 minus 1 gives. So we have x2 minus x1 is equal to. Then we can get rid of these b's in here. So we have rt x2 minus x1. Great. So I can simply write this as delta x small x is equal to rt capital delta x. So delta capital X in here. So if I say that I have, let us assume that the length of del x is L, or small l, and del x, delta capital X is capital L, or let's write it like this, it's L. All right, so delta x dot delta x is equal to RT delta x dot RT delta capital X. And here, you know that this is L squared, right? Because this is L dot L, and you know they're in the same direction, so their cosine is 1, so this becomes L squared is equal to, so del capital X dot, so I can write this as del X, this is equal to del X R T transpose. This is equal to this. If you remember, if you recall from the previous modules. So del X R transpose T dot R T del X. This is nothing but, and this is nothing but I, because we have an orthogonal tensor here. So we have this equal to del X dot I del X. And you know that this actually gives us del X. So we have del X dot del X, which is equal to L squared, or L squared here. So therefore, L squared is equal to L squared. L is equal to L. So you see here that we got this. There is no change in distance between any pair. So I assume the pair here, this is the first point, this is the second point, this is a pair. And then I showed that their length, its length does not change. And current configuration as well as the reference configuration. All right. We also have another example here where it says that, we'll talk about this later, because now we have the combined. We have the rigid body translation and rotation, and now we're going to combine this. So we have an initial configuration here, we translate it, and then we rotate it. So finally, it'll become something like this. So we have a translation as well as a rotation. Great. So we have the general rigid body, motion, as the book indicates. So if we combine these two, this one and this one, because this was the general one, we don't use the origin. We basically do not use origin for the for the rotation. So we discuss this, we get this, and we have this in here, and this in here. So if we combine, this is a star, double star. So combining star and double star. So we get something like x is equal to RT capital X minus B plus CT. So we have this orthogonal rotation this rotational tensor, which is an orthogonal tensor, and we have this transformation tensor, and we have this, arbitrary kind of vector. It says that, okay, your initial configuration, it needn't to be at the origin. And remember that this determinant, the determinant R of RT is equal to 1. This is an orthogonal tensor. All right, and now we're going to solve this example here because I guess that is also another important example. Example 3.62, where it states that, okay, we're going to derive a relation between the velocity of a general material point and the rigid and the angular velocity. So we're going to create a connection between the velocity of a point with its angular velocity in the general form. All right. So if you remember, we said that the velocity, so the general form is x is equal to r t times x minus b plus ct. And if you remember, we said that the velocity is the derivative of, sorry, this one was on. So, all right. So, x. So we have to take the derivative with respect to time. And if we take the derivative of x with respect to time, basically it gives us v, the velocity, and here we have rt, which is a function of time, so we have r dot. So we show the derivative with respect to time with dot, if you recall from dynamics. And this one is basically constant here. So you have the initial vector minus your arbitrary vector plus c dot t in here. All right. So now, from here, I can also write x minus ct is equal to r. Let me just write it with another color. RT times x minus b. So now, if I times each side by R transpose, then I'm going to have RT transpose, then I'm going to have RT transpose times x minus CT is equal to, so R transpose R is basically I. And this is I times x minus b, or simply x minus b. So now I say that this is 3 and this is 4. So we substitute 3 in 4 and we get v is equal to r dot t. So instead of x minus b, we have x minus ct plus c dot t. I guess that I missed this R transpose in here. So this was R transpose T, X minus CT. Perfect. And now let's work on this. Let me change this color in here. So I have R dot T, R transpose T. So I can simply write R R transpose. And if I take this derivative with respect to time, then I get R dot, or I forgot this T's in here, R T transpose. So it's going to be RT dot RT transpose plus R T R T transpose dot. So, and this is basically R transpose. So if you recall, R T transpose was basically I equal to I if R was an orthogonal tensor. Therefore, this is basically equal to 0. So this is 0. So you have I, the identity matrix. So if you take this, its derivative with respect to time, so definitely becomes 0. Therefore, we have R transpose T, R T transpose is equal to minus R T transpose dot, right? This can also be written as, if you remember, AB transpose, ABT transpose was B, so A transpose. So doing this, we get minus R T, the R dot T, R T transpose. So if you recall, so we have this. So now you see here we have a kind of matrix. Let's call it T, for example, T of T, for example. And here we have the same tensor here, T is T, right? And this T of T is basically equal to minus T of T transpose. So a tensor is equal to minus of its transpose. What does it mean? So if you have kind of like this kind of tensor, so 1 2 1 3 2 3, this is minus T, 1 2 minus T 1 3 minus T 2 3. And if you take this, let's say the transpose of this, so you get something like minus T12 minus T13 minus T123, 1 2 1 3 and T23. So if you put a minus here, you will see that this become minus minus minus, this is plus plus plus. So this is equal to this. Therefore, this is definitely an axisymmetric or an anti-symmetric. Therefore, T of T, which is equal to R dot T, R transpose T, is an anti-symmetric tensor. So this is an anti-symmetric tensor. Perfect. All right. So now we know that this is an anti-symmetric tensor. R dot T, R transpose T, is an anti-symmetric tensor, we can write it in form of dual vector. Let's assume RT dot RT transpose is the same as omega, for example, here. So I have this in here. So I have V is equal to omega. So if you, let me just write this. So if you recall, we have TA. If T was an anti-symmetric, so we write it TA cross A. So again, we use this in here. So we have V, we have this omega cross X minus CT. I guess that I missed something in here because V is this. Okay, this is minus C dot T. I just missed this one. Minus or plus C dot T. CT. And what is this? This can be written as R, for example. So we assume this is R, get omega cross R plus C dot T. This is the angular velocity, if you recall from dynamics. So now we have this, and that's it. All right. Great. So next, we have the infinitesimal strain in here. Oh no. Infinitesimal, sorry, deformation. And what do we mean by infinitesimal deformation? So it's supposed that you have a kind of configuration like the one you see in here. And, you know, when the rotation angle is very small, so for example, where we had, for example, we said that, okay, sine, for example, 1 is equal to almost sine of x is equal to x, for example, because we can assume, we can make this approximation where x is very small, so the sine or the tangent of x is equal to x. By this infinitesimal, we mean something like this. So we have very, very or slightly significant difference between, let's say, the current and the reference deformation. All right. So let's suppose that we have our current, sorry, our, let's say, reference deformation, and we have our current deformation. So this is our current configuration, and we have our reference configuration here. And this is our coordinate system. This is x1, this is x2, and of course we have our, you know, this is x, this is capital X, of course, and this is P t0. So you have a particle here at time equal to 0. And you have this particle here in the current configuration using this small x vector here, and we call it this p at t. Suppose you have another, and let me just draw this line here, where it says that the displacement between these two is basically u. So we have u, x, and t. And now we have another kind of, another kind of particle, another particle here, in here, for example, in the reference configuration, where we call it q. So we have q in here, and the corresponding point q here, it's qt0, is here, for example. This is q at t, and their corresponding, displacement vector. Oh, sorry. Is this u here? But we can see that this is changing dx. This one is changing by d small x. Therefore, we have this u x plus dx and t in here. So we have 2 points, p and q, at the reference configuration here. So their distance is dx, and we have the reference, we have capital X vector for the reference configuration for point P, and we have their corresponding points in the current configuration as PT and QT. So this distance between them in the reference configuration is d capital X, and in the current configuration it is d small x. So we have the displacement vector as u of x, capital X, and t, and here u for the point q, t0, and point qt at time t is basically u, x plus dx, and t, which makes sense. So if you recall, we previously had x was small x, or the vector, and in the current configuration was equal to the vector we had in the reference configuration plus the displacement vector. This was basically in the material coordinate. And now we have x plus dx in here. So we have x plus dx is basically x plus dx plus this u in here, this purple line here. So we have x plus dx plus u, which was a function of x plus dx, and t. So if we subtract these two equations from each other, so I have again 1 and 2, or maybe 5 and 6. So we subtract 6 from 5, for example, then we get dx is equal to, so this is dx plus u, x plus dx, and t minus u, x, and t. So if you recall, this was basically this one. if you recall, from the gradient was u. Definition from the gradient definition, it was u x plus dx t minus u x t divided by dx. So if you recall from this, then we can say that dx is equal to d capital X plus, and instead of this, we can write, let me just change the color of this as well as, or maybe here. Perfect. So I can say that this is del u dx. So this is another important equation here, where we call this del u the displacement gradient. Sorry, the displacement, no, displacement gradient. I was looking for tensor. So this is the displacement gradient, because here we have a tensor. So basically del u is nothing but you have a u. Sorry, you have a vector here, u. And this u is basically a vector. So you have u1 in Cartesian coordinate system, of course. In Cartesian coordinate system. Partial derivative of u1 with respect to x1, u1 with respect to x2, u1 with respect to x3. Then u2 with respect to x1, u2 with respect to x2, and u2 again with respect to x3. Partial derivative of u3 with respect to x1, partial derivative of u3 with respect to x2, and partial derivative of u3 with respect to x3. Or in indicial notation, so in indicial notation, you know that dxi basically is a vector, so you have dxi plus, and del u is nothing but partial derivative of ui with respect to xj dxj. This is also important. Perfect. So if you have the displacement gradient, and if you find this is a tensor, this is a second order tensor, and if you calculate this product and sum it up with the current configuration, the reference configuration, you get the current configuration. For this, you can for this we can use we can calculate. Sorry, we can solve a problem here. So we already mentioned that we have to deform the current configuration equal to summation of the reference configuration plus the gradient, the multiplication of the product of the gradient and current configuration. So if we somehow play or manipulate with this equation, we can write this as I, the identity matrix, I dx, the identity tensor, sorry, because these are all tensors, plus del u dx, and I can factor out, sorry, this I plus del u from here, this dx. I call this I plus, or let's call this f dx, where this f is equivalent to I plus del u. And we call f, we know this as the deformation gradient tensor. Deformation gradient tensor. Or maybe it's a good idea just to shift everything a bit down. Right here. Deformation gradient tensor. So basically, I didn't do anything new. I manipulate the dx here. So I wrote it in a tensor form, and I just arrive at this equation here, which says that dx is a dx small x in current configuration is equal to a tensor here, where we call it deformation gradient, and the product of this f, this deformation gradient, and dx. And we know this as f as the deformation gradient. So we have del u as displacement gradient. All right. We already mentioned that we have a current and a reference configuration. And of course, each element in these two configurations has its own length. So let us assume that the length of dx is ds, and, or maybe it's better to write it like this, and the length of dx is basically ds. So this s is capital letter S. So if I do this, I have dx as f as the product of f dx, so I can write dx dot dx is equal to f dx dot f dx. So I can write this as dx f transpose. So I write it dx f transpose f d dot f dx, and this f transpose f is basically dx dot another tensor. We call it c dx, where c basically is the same as f transpose f. We call this right Cauchy green deformation tensor. So this C is basically the right Cauchy green deformation tensor, or simply the right Cauchy tensor. So we already said that C is equal to F transpose F, where F is of course nothing but I plus the gradient of U. So it is I plus the gradient of U transpose I plus del U. All right, so this can be written as I transpose plus del U transpose times I plus del U. And you know that I transpose is equal to I. So we simply write it like this. So we have I plus I del U is the same as del U plus del U transpose here times I is the same as del U transpose plus del U transpose del U. So you can see that C is equal to this expression here, So now we have C in form of displacement gradient. We can uh, basically simplify this further down to C equal to I plus 2E, I call it star, uh, as the book also used for the sake of consistency. And the book says that, okay, where E star is basically this part of the equation. So the book says that E star is half of del U plus del U transpose plus the product of del U transpose del U. And this is called the Green-Lagrange, or as the book said, Lagrange strain tensor. All right, so we had our, our deformation, and we have our relation between the deformation in the uh, in reference and current configuration in form of this equation here, where we had where we created this connection using this displacement gradient del u, and then from here we moved to another equation where we had the gradient, the deformation gradient. So we had a relation between the current and reference configuration using this f, or the deformation gradient. And next, we created a connection between this deformation gradient with the displacement gradient here. And we basically replaced this part of the right Cauchy green deformation tensor with this E star here, where we call it Lagrange strain tensor. And what you see here is basically the complete tensor, the complete strain tensor for, or it's better to say a general strain tensor here. See, it is the, let's say, the general strain tensor, and where we call this basically the green strain tensor. So in order to get the infinitesimal a strain tensor out of this general strain tensor, so to get the infinitesimal strain tensor, we basically get rid of the higher order terms. We neglect the higher order terms of displacement gradient in E star, basically. So, and we show it with small e. So it's better to write it here in infinitesimal strain tensor is basically e, and it is 1 divided by 2 times del u plus del u transpose. So we basically get rid of this part in here. So this is the infinitesimal strain tensor. And if I write this in indicial notation, I have Eij is equal to half times. So this is del u. So it is the partial derivative of ui. And remember here, we have capital X because we are doing everything with respect to the material description. Xj plus, now we have transpose, so I and j should be swapped. So we have partial derivative of uj with respect to xi. Or you can simply write it like u, I, and j plus u, j, and I. All right. So now C for, C for the right Cauchy green strain tensor, deformation tensor, basically for the infinitesimal strain tensor becomes nothing but C is equal to C, let's say, so let's put an approximate here. So it is I plus 2E in here. And let me just put angle around it. So we have this in here. So therefore, if we have two elements, right? If we have two elements and we want to calculate, or let's say dx1 and dx2. So if they deform, and in the deform configuration, they are dx, it's better to use the superscripts. So here I have dx1 dot dx2. So if you want to know what is their angle, so it is basically dx1 dot dx2 plus, here we have, see here we have I plus 2e. So we have C in here, where C is I plus 2e. I made a mistake here. I have seen here because this is dx1 c dx2, which is equal to dx1 dot, okay, this is I plus 2e dx2. So if I expand this, this is dx1 dot dx2 is equal to, oh, sorry, plus 2, I have dx1 dot e dx2. This is also another important equation here. So we basically created a relationship between the deform or the current configuration and the reference configuration using infinitesimal strain tensor. And as I already mentioned, is a second order tensor. It is here. So if I write this, for example, in Cartesian coordinate system, if you remember, in Cartesian coordinate system, so if you remember from your mechanics of materials, we had the partial derivative of ui, ij, This is uxj plus uj with respect to xi. So if we have, therefore, if we have e11, it was half of partial derivative of u1 with respect to x1 plus partial derivative of u1 plus x1. And this is nothing but partial derivative of u1 with respect to x1. Or for example, e12, it is half of partial derivative of u1 with respect to x2 plus partial derivative of u2 with respect to x1. And this is basically the same as epsilon 1, 2, if you recall from your mechanics of materials, that it was half of partial derivative of u with respect to y plus partial derivative of v with respect to x. If you remember, we had this x and y in mechanics of materials, and we said that if you have a displacement in x direction, it is u, for example, and if you have a displacement in y direction, it is called v. So we take the derivative, and they are both function of x and y. This is the same as here. So it originates from here. It is the infinitesimal strain tensor from basically the Lagrange strain tensor, which is also called the Cauchy strain tensor. So if I put, for example, this into a kind of, let's say, tensor, so I have the partial derivative of u1 with respect to x1, which was the same as, if you remember, we had epsilon 1, 1, which was this one. And then I have half of partial derivative of u1 with respect to x2 plus u2 with respect to x1. This was nothing but epsilon 1, 2. So basically we have this also in here because we have a symmetric kind of, tensor here. So E is a symmetric tensor. All right. You can simply write this in the cylindrical as well as spherical coordinate system, because let's say the E or the small infinitesimal strain tensor, because you can calculate del u, the gradient of the displacement, the displacement gradient tensor in any kind of curvilinear coordinate system like spherical or cylindrical. So it will give you the infinitesimal strain tensor. So now let's get into an important topic here, where we're going to understand what are the geometrical, what is the geometrical interpretation of different components on this tensor E in here, because we already mentioned that this is a tensor, like you have E, E11, E12, blah, 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 blah. And we want to know what are what each of these elements actually indicate, and what is their geometrical representation. So let's write in here the geometrical representation or interpretation. Or maybe interpretation of E, of the tensor E. All right. So we divide this to the diagonal. So if this is E, so you have some diagonals and you have some off diagonals. All right, so let's start by diagonal elements. Diagonal elements. So we already mentioned that if you have, let's say a kind of vector field in reference configuration, it is dx1. So you can write it as, if you have like a curve like this, so it has a length like d capital S, and it also have another vector, which is the normal to the surface. So you can write this as its length time n, right? So this is a vector. So we use the same terminology here. So we have dx1 is equal to ds, for example, 1n. And here for the diagonal elements, we assume that we also have dx2, where these two are equal to each other, and we have dsn. So n here is a vector. It is the normal to the surface vector. So, and we already derive an equation here. This is very, very important. I call it black square. So from black square, we have so it is of course clear that the x1 is also equal to dx2. So it also has ds. So ds like something else like m or whatever. It's not important here. So we have dx is equal to, we have dx1.dx2. So it is dx plus 2 dx dot e dx. So this is, since this is dot, so it will get us it will give us a scalar field. So it is ds squared is equal to, and here we have ds capital squared plus, here we have 2, and then we have this dx, which is ds. Then we have a ds also here, so it is ds squared, and we have n dot en, something like this. All right, so now if I just play with this a bit, so I have ds squared minus ds squared, and sorry, maybe ds squared minus ds squared is equal to ds squared times n dot en. Then I write ds minus ds times ds plus ds. So I can break this into this. I have 2 ds squared here. Then this is n dot en. So since we're talking about infinitesimal strengths, so infinitesimal strengths, so we can say that, all right, ds is basically the same as ds. So there isn't that much significant difference between the length in the current configuration with the reference configuration. So there is no difference basically between the small s and capital S. So I can write this as ds minus d capital S. This is 2ds divided by 2ds squared is equal to, so I can get rid of this. So I have ds minus ds capital divided by ds capital, which is equal to n dot en. This is also another important relation. And this is the same as, if you remember, you had, so you said that if you have a beam or bar or whatever like this with a length of 0L, and you just, with a length of L0, sorry, and if you just pull it on one side, for example, so it will expand in L1. And if we want to calculate epsilon, or the normal strain here, for example, E11, if this is X, for example, then we said L1 minus L0 divided by L0, for example, and this will give us the, let's say, the normal strain in the bar. this is the same as here. So you have your deformed length minus the initial length divided by the initial length. So this will give you in whatever direction as you want. And this n here is basically the normal to the surface vector. So this is like, if you have a beam like this, and you pull, this is, for example, x, and this is y, so xy, this is z. So n here is 1, 0, 0, right? So if you want to calculate epsilon 1, 1, it is basically the length L1 minus L0 divided by L0. And this gives you E11. Why? It's because n dot En. And this n is basically 1, 0, 0 dot, and you have your E11 or whatever, then you have 1, 0, 0, right? And this gives you E11, 0, 0. And the dot product basically gives you E11. The rest are 0 here. Therefore, we can say that E11 is basically the unit elongation. Why unit elongation? Because we have this unit vector here, normal to the surface. So E11 is the unit elongation for an element in the x1 direction, as Book also said. And I already mentioned why we say x1. And basically E22 is the unit elongation for an element in the x2 direction. And of course, E33 is the unit elongation for an element in the x3 direction, of course. We call these normal strains, E11, E22, and E33. So let's get to off-diagonal elements. So for the off-diagonal elements, suppose you have dx1 is equal to ds1m, for example, and you have dx2 is equal to ds2n. So you have two different, let's say, vectors here, where we only consider the case m dot n is equal to 0. So they're perpendicular to each other. This is very, very important. We have the case where these two are not, perpendicular to each other or orthogonal, and their dot product is not necessarily 0. So this actually creates some complicated kind of situation, which we're not going to get into in this module and over these kind of videos here. So if we have this, then again, from this black square, we have, if I remember correctly, dx1 dot dx2 is equal to, let's say we had dx1 dot dx2 plus 2, if I remember, 2 dx1 dot e dx2. Perfect. And these two, their dot product is not 0 because we initially assumed that m dot n is equal to 0, but their deform couldn't be 0. So there might be another kind of angle between them. So if you remember, we had, for example, x1 and x2, they were perpendicular, but for example, if this is x1, or I can get rid of this, if this is x1 and this is x2, they're not necessarily perpendicular. That's what I'm talking about. So that's why we don't know anything about this. So we write ds1 ds2 cosine theta, because we don't know anything about this angle. And then their dot product is 0. Therefore, ds1, ds2, m dot n, this is 0 plus 2, ds1, ds2. So we have m dot en. Perfect. So if I rewrite this, we have ds1, ds2 cosine theta is 2 ds1, ds2, m dot en. So due to the assumption of infinitesimal strains or deformation, it's better to say, we can say that ds1 to ds1 is approximately equal to ds2 to ds2 ratio is equal to 1. So these are equal to each other. They're approximately equal to 1. And since dx1 and dx2 are perpendicular or orthogonal, it's better to say, orthogonal, therefore theta is equal to half pi minus gamma. We can make this assumption. Therefore, cosine theta is equal to cosine half pi minus gamma, which is equal to sine gamma, where it can be approximated by gamma because we have infinitesimal kind of deformation. Therefore, we have this ds, so we can divide this by, ds1, the product of ds1 and ds2 capitals here. So it becomes 1. Cosine theta is basically equal to gamma. We finally get gamma is equal to 2m dot en, basically. So as you see here, we have the angle between the two elements. So gamma gives the off diagonal, or gamma gives us the angle between the elements. Therefore, we can say that, for example, if we have m as, for example, 0, 1, 1, oh, sorry, I have to write it in row format. Then I have E, and this is, for example, 0, E, 1, 2, 0, E, 1, 2, 0, 0, and I have N as 0. So it is E1, this is E2, so it is 1. So it will give me something like E12, 0, 0, sorry, 0, 0, this. And this will give me E12, right? And I have a 2 in here, so 2 goes here. So as you see, it will give us the shear or the decrease in the angle, as I already mentioned. The decrease in the angle, if I can find, yes, it is the decrease in the angle. Gamma is the decrease in the angle between two elements, originally in x1 and x2, or for example, x1, x3, x3, x2 directions. So we have 2e12 is the decrease in angle, between two elements originally perpendicular to each other. So originally in the x1 and x2 directions. Therefore, 2e13 is the decrease in angle between two elements originally in the x1 and x3 directions. So they're perpendicular or orthogonal to each other originally. This is very, very important. If we made this assumption in developing these kind of equations that the initial elements are perpendicular to each other. So 2e23 is the decrease in angle between two elements originally in the x2 and x3 directions. So maybe it is a good idea to solve example 3.82. So basically what we have here is a displacement field, hopefully in the material coordinate. This is very, very important because what we developed is in material coordinate, not in a spatial coordinate. If you have this spatial coordinate, you have to just transfer everything into the material coordinate, and then start using these kind of equations that we developed so far. Otherwise, you have to develop your your equations for the spatial coordinates, because we already said that they basically they are transferable. And then we have u2 as k times x1 squared minus x2 squared, and then we have u3 which is equal to 0, where we have k very, very small. It is 10 to minus 4. So here it says that for part A, we have find the unit elongation and change in angle, where you have dx1 is equal to dx1 e1, and you have dx2 is equal to dx2 e2 for the prescribed designate for a particle designated at x is equal to, so it is e1 minus e1, so it is let's say 1 minus 1 and 0. So if we want to find, if we want to evaluate this, let's say this elongation and change in angle, that means E, and E is nothing but basically del U plus the transpose of del U. Or if you look at it, you see that this is the symmetric part of the displacement gradient. So infinitesimal strain tensor is basically the symmetric part of the displacement gradient. Maybe it's a good idea just to write it here. So the symmetric part del U tensor, right? So it's also important. So E, the infinitesimal strain tensor, is the symmetric part of the displacement tensor. Great. So if we calculate del U, we get something like, so the derivative of u1 with respect to x1, which is 2k, then with respect to x2, so it is 2k x2, 0, u2 with respect to x1, 2k x1, minus 2k x2, 0, 0, 0, 0. So del U for this x, for this point, basically is 2k. So it is minus 2k, 0, 2k, this is 2k, 0, 0, 0, and 0. So uh, therefore, E is half of, right? So I have 2k minus 2k, 0, 2k, 2k, 0, 0, 0, 0, and the transpose of this tensor basically just 2k, 2k, 2k is minus 2k, and these are all 0. Therefore, it's equal to this plus this is 2, 4, 2k. This is 2k, 0, 0. The rest are 0. So we see that we have this elongation in, for E11 and E22, and we see that we don't have any kind of shear strain or any change in let's say in the angle, but this is with the assumption that we have infinitesimal strains. So if we assume that we have E star, for example, so this is not necessarily equal to something like this tensor as you see here, where the shear differ where these these terms, these off diagonal terms, are 0. There might be some contribution from them, so this is only based on the assumption of infinitesimal strain or deformation. All right, next it says that in part B, find the form position of dx1 and dx2. So if you recall, we have dx1 is equal to dx capital X1 plus we have del u dx1. So I have dx1, which is basically here, this dx1, E1, 0, 0, plus del u, which is, where is it? Okay, 2k minus 2k, 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 the rest are 0, times dx1, 0, and 0. So what we get is basically dx1 plus this times this, 2k dx1, and then we get 2k dx1 and 0, if I'm not mistaken. So this can be written as 1 plus 2k dx1, and this is 2k dx1 and 0. So if I do the same for dx2, I have dx2 plus del u dx2, which is equal to, so I have 0 dx2, you can see it here, it only has e2 component, or plus, this is 2k minus 2k, 0, 2k, 2k, 0, 0, 0, 0, and this is 0 dx2, 0 is equal to, so this is basically 0, and this is minus 2k dx2. This is dx2 plus 2k dx2, and this is 0, which is equal to minus 2k dx2, and this is 1 plus 2k dx2. All right, so let's see what are these. What is the geometrical representation or interpretation of these two deformed, vectors? All right, so let's plot kind of, coordinate system like this. So we have x1 in here, sorry, x2 in here, and then we have x1 in here. So you see that we have an initial x1 and x2, for example. So this is dx1 and this is dx2, for example. Right? So we have something like these in here and here. And then you see that dx1 is deformed to 1 plus k2, which is a positive value, dx1. So in x1, so it is 1 plus, let's say that, for example, it becomes something like this. This is 1 plus 2k, for example. And then in x2, it is 2k. So 2k, for example, here it is 2k. So finally, sorry, this one is better to write it here. So this is 2k. So this is dx1. And then we have another color maybe. Perfect. Okay, then I have minus 2k dx2. So minus 2k here. And then I have, this is 2k, of course. So it is minus in the opposite direction of x1. And then 1 plus 2k times dx2. So we have something like this, for example. This is 1 plus 2k. So we finally have something like this. So this is dx1. So as you see here, we have an angle here, beta, and we have an angle here, alpha. So if I write alpha is equal to 2k, or maybe it's better to write it tangent alpha, where alpha is very small or infinitesimal. So alpha is equal, or tiny, sorry, or alpha is equal to tangent alpha. So we can say that it is 2k divided by 1 plus 2k. And if you write the Taylor series expansion for this, you get something like 2k times 1 divided by 1 plus 2k. And then you get 2k times 1 plus some higher order terms, and then finally you get 2k. You can approximate this with 2k. And also, if you do the same for beta, you get 2k divided by 1 plus 2k, which is approximately equal to 2k. And I have to say that you have, of course, 2 in here and here, and you have, of course, dx1 and dx1 in here. So you see that alpha is equal to beta in here. So this is the same as what I already mentioned here from your mechanics of materials for the development of the engineering strain, shear strain in here. All right, there's also another important example here I want to clarify, and that is the example 3.83. So this example says that if you have a displacement field of u1 equal to kx1, u2 is 0, and of course u3 is 0, where k is very, very small. So it is 10 to minus 4. So it says that for part A, calculate the diagonal AB. See this figure? So we have a figure in here. All right, so this is x1 and this is x2. So we have a figure. All right. So it says that you have a B, where this is 1, for example, and you have this A, B. So we would like to know how this A, B is changing in the deform configuration. So you have the initial configuration where this is square root 2. So we want to know what is its length or how it deforms this AB. For example, you can think of this as like a truss kind of structure. So it is loaded under this displacement field. So we want to know how this actually is deformed. So for part A, it says that use the infinitesimal strain tensor E. So for this, we have to first calculate del U, which is basically the partial derivative of this field with respect to x1. So this is k. The rest are 0, of course. And E is basically half of del U plus del U transpose, which is equal to. So this is the same as the transpose because this tensor it has the same. So this is the same for the transpose. So we have 2k if we sum them. So finally we get k 0 0 0 0 for the rest. Perfect. So we see that this actually elongates in x1 direction with a value of k, right? So, but we want to know, okay, how this AB actually is changing. So first thing first, you have to extract. So we have to find the unit vector. We have to find the unit vector in let's say in AB direction. Think of it like this is, for example, your part. This is AB, for example, and this definitely has a cross section, something like this. So you have to find AB, the normal in AB direction. This is A, this is B, and this is, for example, the cross section, right? This is the cross section. So you're gonna find N in the direction of AB. So that's why we are curious to find this N in A, B, for example. And why? Because we need to know N dot En, right? It's NB, this is NB. So this is equal to, so NAB is nothing but, this is square root, so this is nothing but, the square root is this divided by 2, because this is, 1 divided by a square root of 2, so I just simply rewrite it as this. And then we also have a component in y direction, and this is 0, times, or dot, sorry. We have k in here, 0, 0, 0, 0, 0, 0, 0, 0, and then n again. So we have square root of 2 divided by 2 again, and then 0. So what we get here is basically, this is square root of 2 divided by 2 again, 0 dot. So we get k square root of 2 divided by 2, and the rest are 0. So finally we get k divided by 2. So this value is basically k half. This is the unit, this is basically the unit elongation in n direction, NAB, right? This was the unit this k, basically it's better to say, maybe I just highlighted. This was the unit elongation in x1 direction. This is very, very important to distinguish between these two. So this is how your member, or I don't know, AB, for example, let's say AB, sorry, AB elongate in NAB direction, in the normal direction of AB. But in, for example, in x1 direction, it will elongate as K. So if we want to know how it elongates in 2, so elongation, sorry, in x2 direction, x2 direction, then we have, let's say, n dot en, and this n again, this time is 0, 1, 0, because it is E2. Sorry, I have to write it in row format. I have k 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. This is dot, of course. And this is 0, 0, 0. So it is 0. Perfect. So that's why if I, for example, write this, I can see that it is elongate in K1, the value of K, for example, and 0, this B, for example, in with nothing. I mean, with no change in height to this B prime, for example. And I can say that this is the deformed configuration, right? Deformed. And this is initial or base or reference configuration. All right. There's also another topic which we already discussed, and it's very, very simple. And it's the, do you know the eigenvalues and eigenvectors yeah, of a tensor? Since E is a symmetric tensor, so we expect that it has, you know, three eigenvalues, and it has also three real, and it also has, sorry, real values. We expect it to have three real, you know, eigenvalues and three vectors. So we call them principal strain. This is the same, you know, let's say, concept from the same concept that you learned during the mechanics of materials, where you had the Mohr circle and you found the maximum, and you found the maximum stress and the strain, the principal stress and the strain. This is the same. So you know that E is a symmetric tensor, Therefore, you expect it to have three principal values, E1, E2, and then E3. Where you can find these basically from what you learned from, you know, previous module on the eigenvalues and eigenvectors. So therefore, there exist, you know, three perpendicular in the deform. So you have, for example, you have x1, x2, and x3. So these are, your reference configuration. Therefore, for example, you have x1, x2, and x3. You have three, direct normals or eigenvectors where they are mutually perpendicular. You can easily calculate this, and from here we develop another kind of, uh, let's say, concept, which is the dilatation. So if I move this in here, so we have dilatation. And simply dilatation is the change in the volume. So, for example, you have your current configuration like this, and now its volume is changed, for example. It became something like this. So you can calculate the dilatation using these expressions that I'm going to derive in here. So first thing first, we know that if you recall, we have, for example, if you have like, N1 and N2, or maybe T2, T1, you have this N in here, that N dot T1 cross T2, it gives you the volume of a tetrol of a parallel pipe, which is basically formed by these vectors in here, something like this. So we use the same concept here. So we have the first is, so if we have the length as the first, very, since we are talking about elements, so we have dx1, dx2, and dx3. Therefore, here we have dx3, dx1, and dx2. Therefore, we have dx1 is ds1 and 1, for example. We have the dx2 is equal to dx2 and 2, and so on. So here we can say that v1 is ds1, ds2, ds3, which is basically the same the initial values of ds1, for example, ds2 and ds3. So we simply multiply these two, and v2 is nothing but ds1. So for example, because it expanded, for example, ds1 plus this value times e1. So you have this principal strain because you had three principal directions which were mutually perpendicular. We are going to change E into this kind of tensor, which is E, which can be easily manipulated and dealt with for the case of dilatation. So times ds2 plus ds2 E2 times ds3 plus ds3 E3. Or simply, we can factor out ds1, ds2, and ds3 times 1 plus E1, right? This is the initial, and this is the change in deformation, times 1 plus E2 times 1 plus E3. So if we show the dilatation using the letter E, for example, we see that we have v2 minus v1 divided by the initial velocity, right? And everything is in dv, sorry, since we are talking about very small elements, dv1. This is dv1 and dv2. So here we have ds1, ds2, ds3 times 1 plus e1, 1 plus e2, 1 plus e3 minus ds1, ds2, ds3 divided by ds1, ds2, ds3. So if I factor out this multiplication of ds1, ds2, and ds3, I'll get something like 1 plus e1 times 1 plus e2 times 1 plus e3 minus 1, which gives, okay, this 1, which is the multiplication of these ones in here, goes with this one. So I get something like e1 plus e2 plus e3. So it is like, the multiplication of 1 with this, that, and then some higher order terms. Like, for example, e1, e2, e3, and something like this. We're going to neglect these terms because they're simply, because we simply are dealing with, let's say, infinitesimal strains. So since we are dealing with infinitesimal deformation, we can neglect the higher order terms. So E can be written as the summation of E1 plus E2 plus E3. So as you see here, the summation of E1, E2, E3, or if you remember from the first module, this first invariant of E, which was, if you remember, it was I1, the summation of E1 plus E2 plus E3. Sorry, E1, 1, E2, 2, and E3, 3. Because we had it like E1, 1, E1, 2, 1, 3, E2, 2, E3, 3, and E2, 3. This is symmetric. So the summation of the diagonal elements here simply give us the dilatation. And if you want to calculate this for, so if you want to write it here, so you will have something like an initial notation. It is EII, which is basically the divergence of u, if you remember, which was basically the summation of all the diagonals. So it was the partial derivative of ui with respect to xi. So it is just a number. It's a scalar. So 0th order tensor. So if you if you have the the divergence of u in different coordinate system, you will be able to calculate dilatation and spherical and cylindrical coordinate system. So the final topic here is the asymmetric part of the road of the, let's say, displacement gradient, because we already mentioned that del u is a tensor, and every tensor can be written in the form of a symmetric and anti-symmetric tensor. So the symmetric part was the infinitesimal strain tensor E here, as we wrote it here. So the asymmetric part of the deformation, the displacement tensor, is called the infinitesimal rotation tensor. So we have the infinitesimal rotation tensor, or simply it is the anti-symmetric part of del u, or the displacement gradient. So we already mentioned that dx is equal to d capital X plus del u dx. And this dx, this del u can be written as e plus omega dx. And this omega is the anti-symmetric part of del u. This is the symmetric part. And since this is the anti-symmetric part, so basically omega is half of del u minus del u transpose. And simply, since it is the anti-symmetric part, we can use the dual vector concept here. So I can write, so therefore, I can write, for example, omega dx is equal to the dual vector part of omega cross dx. This is cross, remember, this is the cross product, so it is not x. Therefore, if I have, this, so where ta is the anti-symmetric part, is the dual vector, is the dual vector of omega and is, so we have ta and is, so if you remember, ta was, if we had 1, 2, 3, 2, 3, 1, 3, 1, 2, minus, so it is omega 2, 3, e1 plus omega 3, 1, e2, and then we finally have omega 1, 2, e3. So remember that del u can be written as the summation of two other tensors. Just draw a line here and here. So remember that del u, the displacement gradient, can be written as the summation of the symmetric and anti-symmetric part, E plus omega here, where in E we had elongation as well as, changing angle. Since in omega all the diagonal elements are 0, we only have changing angle or rotation. This is very, very important. There's also another important topic about the divergence of u here in dilatation. So sometimes the divergence, it might become 0. So the dilatation is 0, but it doesn't mean that you don't have any kind of, uh, deformation. So for example, suppose you have a case here, you have a cube, but this cube is deformed under some kind of shear deformation, something like this. So for example, the initial volume is 1 here, and the deformed volume, and the initial volume is 1. So you don't see any dilatation because divergence is equal to 0. There is no difference. So 1 minus 1 divided by 1 is 0. E is 0. The divergence is 0. But you see that you have some kind of, strain or deformation generated in your, your domain or your, let's say, configuration. Therefore, bear in mind that if divergence is equal to divergence, zero divergence does not mean that you do not have any deformation. So zero dilatation or the divergence u is equal to 0 does not indicate zero deformation. we will discuss, you will understand, or you will learn more about this in your elasticity course, where you see that your, for example, your domain undergoes the Vittori kind of stress, where they do not change the basically the volume, but they deform the your domain or your configuration. So these are, the kind of stresses that they it doesn't cause any, change in volume, or they give zero divergence. But they're definitely, they definitely cause some deformation. So this is all about, the infinitesimal kind of uh, deformation and a strain tensor. I hope you'll learn something new. And let's see.